their current treatment plant and evaluated it to see where they're having problems and what they're doing wrong. So this is Stream. He's going to go ahead and talk about the schematic of the plant.
Thanks, Jana. As Jana has already mentioned that it's one of the sophisticated treatment plant in Kampala out amongst the 4 treatment plants, and for some reason it's ineffective since the civil war. So we are going to analyze why it is ineffective and is there any way to optimize the efficiency of the existing treatment plant. So as you can see that wastewater is going to the primary, secondary, tertiary. They have a very good primary, secondary, tertiary treatment, but it's ineffective. So particularly in this area, the anaerobic zone, anaerobic region, it's ineffective. That's the reason why the effluent from the trickling filter is having high BOD, which is 65 mg per liter, and coliforms as 15,000 per 100 ml, which is a little bit more than the local recommendations. So that's and also as Jana mentioned that Lake Victoria is used as a drinking source, and this effluent is sent to the Lake Victoria, which is 5 kilometers from this plant. So our main aim is to optimize the efficiency of this secondary and tertiary treatment plant. So during this process, we went through different secondary and tertiary treatment process, and we developed a flow chart for every treatment against the fixed environmental characteristics, technical characteristics, sustainable features. So we are going to, our main aim is to design such a feature that it should be technical, economical, and sustainably feature design. So for example, if you take for UASB, your upland aerobic sludge blanket reactor, so we analyzed its performance efficiency basing on how much cost it is involved in making it, and what type of operation and maintenance are required. Is it available locally, or any skilled labor are to be required? So these are this is the matrix we followed, and as you are familiar with those symbols, red, green, and yellow, these are just the traffic signals. Red means ready to good to go, wait, and yellow means wait. There are some potential barriers. You have to clear some barriers before going, and red is not good. So we are using the same type of matrix for the tertiary treatment as well. We are and the tertiary treatment options we are considering is drying bed, co-composting, composting, and disinfection. And after the tertiary treatment and secondary treatment with the matrix evaluation, we come up with a feasible design. And as of now, this is the preliminary recommended option with the considering factors which we have, and waste stabilization point as the secondary, and composting as the tertiary. So, but however, our story did not end there. Still a lot more to do, and now I hand it over to Anne to start the story.
Thank you, Shrikant. So basically what we're trying to do now is take what we've learned from the centralized plant and focus more on the decentralized regions, such as the area around the edges of Kampala, where there's a lot of slums, or more rural areas where there is no access to a drinking water treatment plant or anything. So it's more really of a community-based size. So 15 meters cubed per day is a good size effluent. And we want to focus on these areas and just develop a solution that we can adapt to all over Uganda. So now we're just going to go through several of the options that we'll be considering. The first is composting and co-composting. They're a little bit different, but I'll explain that in a minute. Essentially, composting is taking the solid waste from your fecal sludge and mixing it with a carbon source, either like vegetable scraps or wood pieces, or in the case of co-composting, you actually mix it with paper waste from municipal solid waste streams, which takes care of 2 different waste streams in one. Composting doesn't require much skilled labor, but you do have to hire people to mix it and maintain the carbon, nitrogen, and moisture balances. However, it's a very good alternative because the heat generated within the compost pile will kill any pathogens, and then the product that you get out of it is agriculturally feasible as a fertilizer.
I'm going with another technique for the decentralized treatment, pyrolysis, which we all know that it's just a thermal degradation of the sludge at a temperature of around 350 to 500 degrees centigrade, and at that temperature pathogens get killed. So that's one of the desirable requirement which we need, which we choose for. And the other benefits include it reduces the volume of the solids, and the nutrient from the pyrolysis process after some additional treatment is the sludge is rich in nutrients, and we can use it for economical value. And why we choose pyrolysis as this reason? There's reason because it's worthwhile to mention now here that Uganda is having very solar, is rich in solar radiance potential. So it's just using the renewable energy of sun and making the pyrolysis to happen by the solar energy, And there are some technical and economic consideration for design of these paralysis chambers. So the race from infinity converge at the focal point and place that paralysis chamber at such a point where the most of the energy is considered. That's one of the technical considerations to be taken into care while doing this paralysis process.
All right, now I'm going to talk a little bit about urine separation. It's a preliminary treatment, so it's actually installed to the latrines themselves. You either put a toilet on the seat or have like a separate urinal where the urine is drained into either cans or it can be put into a diversion system, which is like a filter where it allows the dry to sit on top and the wet to go to the bottom so you can filter it out. The reason why we would look at urine separation is that if you add magnesium to it, you create magnesium ammonium phosphate, which is also known as stervite, which is a fertilizer that can be used for agriculture, so that could allow them to have a revenue from the fertilizer from the urine itself. Another one we're looking at is planted drying beds. There's unplanted and there's planted drying beds. So what it is, it's a bed with sand and gravel, which drains into like a tube at the bottom, which is like drains out all like the water, and the dry sludge, or like the urine at the bottom, and the dry sludge on the top can stay there for 5 to 10 years, and then after that, due to the plants, it removes a lot of chemicals, and you can directly apply the sludge to fertilizer. So that is really good because they can create another revenue from it, and it's low maintenance, and you just need a little bit of land to create it, so that will be good for them too, since we have a lot of land to work with. And this is Hewitt, and she's going to talk about the DWAT system.
Thank you, Jenna. So the DWAT system stands for the Decentralized Wastewater Treatment. It's an independent system that could be installed for up to 1,000 meter cube treatment per day, which is well above our limitation for design, which is 15 meter cube. So we can use both domestic and industrial wastewater to treat with this system. So it uses settlers and baffle reactors, and the result of this would give us water for irrigation, which is within the guidelines of the WHO for BODs and CODs, and also the solid matter we can use as planted drying beds, which Jenna just mentioned. The disadvantage of this is there's actually no information about it beside the company that actually builds it, so it's not necessarily much used system. Another thing we looked into is tiger worms and soldier flies. We picked tiger worms because they have the ability to consume about 1 gram of the compost per day, which is pretty good, and also they have a pretty good range of pH they can live in. And also the temperature, they can survive between 23 to 30 degrees Celsius, which is the temperature range that we find in Uganda. Another thing we wanted to use is soldier flies, which is, we're going to be using the larva of the soldier flies. We chose this because they actually have the ability to compost a lot of compostable and decompostable minerals before they actually have the chance to decompose themselves, which reduces the amount of odor that could be released significantly. And also they have the ability to make the environment unsustainable for a lot of flies, such as mosquitoes and such, to survive in. So that's also beneficial for the environment. So from all the treatment systems, and we looked at for both centralized and decentralized, the reasons we looked at them is because as far as agriculture go, everything within the treatment system we're planning to build will be used for agriculture, and there will be no waste to consider. And also for health benefits, and since most of the sledges actually end up in the environment without being treated, that's going to be beneficial for the environment, as well as reducing the BOD and CODs that's going to be released into Lake Victoria is very beneficial.
So just really quickly, I'm going to cover some of the not so interesting aspects of this project. The first is our work plan. These are all of our internally and externally imposed deadlines. The next coming up is, as you can see, the written alternatives assessment on March 14th, and we will be back to present that the week after, March 19th to 21st. And also, I'm going to talk about some of our quality controls. We're having weekly update meetings with both our faculty advisor, Carl Linden, as well as our contacts abroad in Uganda and Peru, and just keeping them up to date with what we're doing so that we stay on track. In addition, our internal review process allows us all to go over each of our deliverables and ensure the highest quality product possible. And then, as far as our budget goes, we are charging a fairly standard consulting rate of $50 an hour, and we each agree agreed to work for 15 hours per week. So over the course of 15 weeks, that gives us a consulting fee of around $45,000. In addition, we are including a travel budget so that we can go on site and kind of assess and do some audits and assess what options are feasible in Uganda itself. So between the consulting fee, travel expenses, and miscellaneous budget, our total budget is $55,400.
Okay, so just to wrap it up, in general, we went over like a few of the already existing treatment plans and what we're planning on, and this is sort of our goals for future work for the semester, things that we want to focus on. First of all, social acceptability, putting in some type of treatment system where the culture is going to accept it and use it. If we try to put it in, they won't use it, it's not going to work. Cost is a really big one, so distributing the cost of capital input or generating some type of revenue, like we said, from irrigation, water, fertilizer, and putting into the local economy to keep it going. Weather is a big one, so using different climates, different weather models, and different type of treatments are more amenable to sun or rain or wind. So looking into that, and then obviously we're focusing on more the decentralized treatments that we had mentioned in the end, rather than the treatment plan itself. And then public awareness is the big one. So educational programs for the people there about sanitation in general, making sure that people aren't using the bathroom in public areas, discharge obviously into drinking water sources and whatnot, just heightening the sanitation awareness and making them understand why they need to implement these systems. And that's just sort of a global objective for our company, is to have something that's sustainable and that is practical for the people and that will take care of the waste and sanitation issues there. So we're GWS again. I'm Emily. This is Shri, and Hiwat, and Jenna. And thank you all very much for coming and listening, and we would love to answer any questions. Yeah, Eli?
I can't remember who it was, but someone mentioned that an affluent of 15 meters cubed per day was good. I'm really used to around here, parameters for states. That seems really low. Was that solids or was that all waste?
That I think I mentioned that point. So 15 meters cubed was just the total sludge that goes into the system. I misspoke when I said effluent.
Cool.
15 meters cubed per day, and that's just at the community level for a decentralized region.
Cool. Thank you.
Yeah, Keith.
So you guys said you use magnesium to produce your fertilizer. Do you know where that magnesium would come from?
Yeah, we're looking for potential distributors over there actually, and we should look for magnesium, which is, we are just proposing the technique. It should be economically feasible as well. Though struvite is very rich in, it's almost rich in 98% of magnesium ammonium phosphate, the precipitate from that reaction. So we're just looking for the economy of it as well.
So the worms and the flies, where in the process were those added, and do they have to be repeatedly added?
That one we're actually still debating whether to put them in the primary treatment of sort of the primary treatment while the sludge is still sitting, or to use it as tertiary treatment after we get rid of most of the things we could get rid of. So once we decided the different form of treatment we're going to use to treat those things, we'll decide whether to put them in as primary or not.
Because one of the problems that we're facing is people use latrines as trash cans. So we have to actually try to get a percent of what's made up of sludge, what's made up of trash, and what's made up of other things. So once we figure that out, we'll see where we can install the flies and worms.
You mentioned something about the sludge treatment where it sits for 5 to 10 years. Does that look like a kind of basement? Could you just continually add it, add on top, and the plants continue growing?
Yeah.
And then when it's full, you let it sit?
No, so what it is, it's kind of like a wetland. So you just keep applying it to the top. It's going to start to use up some of the nutrients in the sludge, but after it says from 5 to 10 years, but it depends on what your input is going to be. But since we have such a small input of what we have is so small that we can actually average it out to be about 5 years. So that's what's good about it, because we don't have to deal with it right away, but hopefully over time we can start to use it and have a market that is dependent on it.
In the same vein, so what type of plants would be grown in something like that, and can you harvest them? I'm not sure if you mentioned that.
There's a few different options. With like constructed wetlands and whatnot, cattails are used frequently. It's kind of a neat thing actually about Uganda where we're looking at. They eat a lot of tomatoes, and then the tomato seeds end up in the sludge, and they actually grow tomato plants out of those beds. So it's kind of like you don't have to input it, you don't have to do anything. They just start growing because they're already in the sludge. So that's a main source of plant, and it's actually a neat way to keep reusing and get something out of the system is you have viable tomatoes from your drying beds. So it's actually unique.
I could just be coming out of nowhere, but personal care products, how much is this system going to be affected by that? And like solids, like toilet paper, or other sort of things that are waste that go down.
Okay,
That's
so
actually
for centralized treatment, as we mentioned, that we are going to implement the bar screens on the grid chambers as well, which removes the solid part, so that the rest of the effluent sludge, goes to the secondary treatment plant. So at the primary stage itself, we try to remove that solid part, as you mentioned. It's worthwhile taking care of that as well, because it's going to affect the downstream process as well if you let that through the secondary and tertiary treatment.
And then for the decentralized, that's one of the reasons why we wanted to look into co-composting. So we'll be able to take care of both the sludge and any solid matter that actually will end up in the
Anyone else?
Thank you.
Thank you.